Launch your spacecraft from within a mountain. They could dig a deep vertical shaft inside a mountain, bringing you closer to the thermosphere. With engines igniting 1,000 feet above the launch site, utilizing maglev and railgun technology, or even the innovative coil gun technology, could be a game changer. Launching Starships from underground offers protection from the elements and could significantly reduce fuel costs. It's a fascinating and efficient approach to space exploration. We do this with submarine nuclear missiles, so why not do it for Starships? Watch that you are not close to a fault zone, and breaking the sound barrier near commercial airspace will pose a problem. That is all that I am willing to share at this point. Reverend Johnny Warrant.
Hello everybody and welcome back to Space Doc. I'm Hujuana and today we're looking at electromagnetic weapons, because I have some fun advanced ones to share with you. But more on those later. First, let's lay out rails and coils and their pros and cons before mixing everything together to see what's best. Railguns and coil guns are the two big options for realistic future weaponry, since electromagnetic systems are capable of attaining much higher projectile velocities than good old chemical propellant. Higher velocity is particularly important in space combat because increasing projectile velocity directly increases effective range. Also, big numbers are cool, as are railguns, which are made of parallel conductors, the rails, and a sliding conductive armature that bridges the gap between them. This armature can either be pushing the intended projectile or be the projectile itself. Electric current is sent up one rail through the armature and down the other rail to complete a circuit. This loop, like any active electrical circuit, has a magnetic field associated with it, but the field goes in opposite directions along each rail. This produces a Lorentz force, a fancy name for electromagnetic force, that does two things: pushes the rails apart and shoves the armature down the rails. The more current that gets dumped through this circuit, the higher the Lorentz force and the faster the projectile will get yeeted. Technically speaking, this is very simple. The most complicated bit is generating and storing enough current to reach high velocities. The main challenge with making a good railgun is instead the materials used for the rails, since those being eroded is the one big downside these things have. This erosion occurs primarily from friction, since the armature is going to be in direct contact with the rails as it slides along them. Yeah, this happens in normal guns and isn't much of a problem there, but the extra high speeds in a railgun means extra high friction. Unlike normal guns, there are also electrical arcs between the armature and rails wherever there's a gap. This is another source of erosion, particularly at the muzzle. I'm not sure, but I think that's where these flames are coming from. It's all burning vaporized metal, a great demonstration of why rails need replacing now and then. We know all about these issues thanks to the high technology readiness level of railguns. Multiple nations have done serious research into making usable weapons out of them. If you're even vaguely into railguns, you know that the US Navy looked into them a few years ago. But while they stopped bothering, the Japanese and Chinese developed their own, and both have test weapons currently installed on ships. So that puts rail tech somewhere up around TRL 7, close to being a mature technology in actual use, which is relevant for us due to comparisons we'll make later. Now we have coil guns, which are still electromagnetic but work on different principles to railguns. They're still pretty simple though, with the projectile being pulled towards an electromagnetic coil when it gets turned on. Right as the projectile reaches the coil, the electricity is turned off and the projectile sails onward on its own momentum. The one coil makes this a single-stage coil gun, which does work, but we can do better by just adding more coils that are triggered in sequence. Compared to railguns, there are some obvious benefits, such as the projectile being magnetically levitated in the barrel, meaning there's no friction to slow the projectile down or wear anything out. The technical challenge here is in getting the timing just right. There's a very small sweet spot for triggering each coil to get optimal acceleration of the projectile, and hitting that spot gets harder and harder as the projectile moves faster and faster. And how do you even trigger the stages? Do you just set the coils to go off on timers and hope it works out? Or do you have something that measures where the projectile is as it moves and dials everything in just right? On that train of thought, there's other considerations too, like how you deliver power to the coils. With a railgun it's easy, you just dump power through the back of the rails, but with a coil gun, do you run each coil off its own capacitor, or all of them off one absolute unit? With all that said, there have been various experiments and proposals for things like electromagnetic mortars and such, but nothing as concrete as the various naval railguns that have been built. That places the technology readiness level somewhere around the middle, maybe around 5 or 6. Coil guns clearly work and are out there, but so far the ones that exist are a bit gimmicky and don't have much of a use case when put up against other options. Which brings us around to the first of those advanced weapons, a hybrid between railguns and coil guns, the helical coil electromagnetic launcher, which is a bit of a mouthful to say. Because of that, we'll just follow the precedent from the Galactic Library article on them by Luke Campbell, which refers to them as helical railguns. Here's how they work, using this cool art, again by Luke Campbell. They have 2 rails that run the length of the gun, but around them is a helical wire barrel, which is where the name comes from. Electric current goes down one rail and then passes into the projectile, magnetizing an electromagnet contained within it. After doing that, the current moves forward into this first radio contact and out of the projectile into the helical wire, making that an electromagnet. It spirals its way up the helix and into the second radio contact on the projectile, which passes it back to the second rail, completing the circuit. The motive force comes from the interaction between the electromagnetic coil inside the projectile and the section of helix outside it that is also magnetized. In our example image here, the magnetized part of the helix is ahead of the magnetized part of the projectile, which gets pulled forward. The clever bit is that as the projectile moves, the radio contacts on it also travel forward, magnetizing a continually moving section of helical wire and keeping the pull constantly ahead of the projectile's own magnet. So you can see what makes it a hybrid. Energy is delivered to and through the projectile via the rails, but the thing that moves it is the exact same thing as from a coil gun. If you make one with the 2 electromagnets swapped around, putting the magnetized helix behind the projectile, you can push it forward with repulsion instead of attraction. Or you could run the current through the circuit backwards, accelerating the projectile in the opposite direction. Not sure why you'd ever want to do that, but it has been demonstrated experimentally with this alternate design where a projectile with a hole in it runs down a helix in the middle. So what are the pros and cons of helicals? Well, there's no mucking about with getting timing right, since it's a continuous system, just like with a railgun. But there is a lot of contact going on since both the rails and the helix need to touch the projectile. However, since only a small section of the whole system is magnetized at any given time, a helical needs far less current to reach high velocities, which should mean less erosion. This lower energy requirement has another benefit, since it may be easier to equip them on vehicles smaller than ships, or even go right down to practical small arms. Another downside is that the projectile is a lot more complicated. A railgun's armature just needs to be a chunk of something conductive, and a coil gun can fire pretty much anything ferromagnetic. For a helical, you need to have the coil and the contacts all going up and down, messing with whatever your projectile might be made of. Though, to be fair, you could just have it be like a sabot, pushing along whatever the actual projectile is inside of it. The thing is, this is all conjecture, because the technology readiness level of these things is kinda bad, way down at 4 or even 3. More research into them needs to be done, and all sorts of unknown issues might crop up that may put a damper on weaponizing the tech. But maybe rails and coils and helicals are just not good enough for you. Maybe you want something faster or a bit more exotic. Well, for that I have Professor Winterberg's electromagnetic rocket gun, which sounds a bit like a magic spell, but is a theoretical way of boosting the armature of a railgun by stuffing it full of coolant. As the armature gets heated up from all the electromagnetism and friction, it evaporates this coolant, which expands and shoots out the back, just like a rocket. Since this happens inside the powerful magnetic fields of the rails, that evaporated gas gets ionized, allowing an electrical arc to pass through it, behind the projectile. This arc turns the gas into a plasma, heating it up and expanding it even more, pushing everything ahead of it even harder, potentially reaching absurd muzzle velocities far exceeding what a normal railgun can achieve. The cost is a lot of rail erosion from that extra arc, and you need a proper gun barrel to contain all that gassy plasma stuff. No cool gaps between the rails here, I'm afraid. The bigger downside though is that this is only theoretical. No one's ever tried to experiment with this idea, so it's got the lowest technology readiness level of anything we've talked about today. But fiction is free of that little requirement. Stories and world building can go wild with these very real technologies, as evidenced by all the railguns and coil guns seen all over the place. Perhaps in future, helicals and EM rocket guns will have their day in the sun as well. You can support Space Dock by joining our Patreon, where you can get our frigate and spacefighter design reference books. Alternatively, you can support us directly through YouTube by becoming a channel member. Thanks to our supporters, and thank you for watching.
Let's see how this works. Step number 1. The submarine will ascend to an assigned depth. Step number 2. When ready to launch, it will open of the hatch and the protective seal will break open. Step number 3. High pressure and compressed air is pumped into the tubes, and this is used to eject the Tomahawk missiles. Step number 4. The tip of the missile breaks the water's surface. Step number 5. The rocket boosters fire and propel the missile into its path. Boosters fall off as soon as the missile is out of the water. Step number 6. The main engine of the Tomahawk missile will engage, and then it will open its wings, just like the animation shown here.